Hey, welcome guys. Today we're doing 4.4 continued. So we're talking about properties of rational functions. So we're looking at asymptotes today. So the vertical asymptote, it occurs at undefined values for our function. So it has to do with our domain. And then vertical, what it is a vertical line that the graph does not cross. So if, for example, we're looking at this, right? We're considering the domain of this, and we know that x cannot be equal to positive 3. Right, because 3 minus 3 is 0, we can't have a 0 there. So what that tells us is that where x is equal to 3, right, there's your x-axis. We have a vertical line passing through here that our graph is not going to cross. Okay, and then our graph from there might look like, for a rational function, it might look something like this. Oops. Yeah, it might not be exactly like that, but it might look something like that. So there's a line in there that the graph doesn't cross. And it doesn't cross it because it's undefined at that point. Now, not to be confused with a hole. So if we have something where our factors can cancel, so look at x plus 1 over x plus 1, x minus 2. What would happen in this case is our x plus 1s would cancel. We still have a 1 technically in the numerator. So if they cancel, where x is equal to -1, right? Because -1 plus 1 is 0. There'd be a hole there. So this one might look like, well, there's an asymptote for sure at -2. So we draw our asymptote at -2. Let's change colors here. And then it might look like this. Right? But at -1, there'd be a hole in there. Now, if you did graphing calculator, or if you did Desmos, it would draw the graph, but it really wouldn't show you the hole, like unless you clicked on that specific point, and then it would say -1 comma undefined. But if not, it's not going to show you a big hole like that. But if you were to graph it, you'd draw it that way. And it's just important because sometimes they ask you for asymptotes, not holes. So if they're asking specifically for asymptotes, a hole is not technically an asymptote because it cancels out. And we'll see more of that later. Okay, so find vertical asymptotes. This is pretty much what we're doing last time, right? We're just finding the domain restriction. So for this one, what minus 1 is 0, so that's 1. Remember, when you write your vertical asymptote, though, you have to say x equals 1 would be our vertical asymptote, right? So you have to say x equals to give us your vertical asymptote. Okay, we did this one before, but let's do it again. X squared plus, minus 4. We said that we can set it equal to 0 to solve. So we're going to add 4. And we're going to square root. Oops, not x squared. X equals positive and -2. Right, so this one is solved. So we have two vertical asymptotes, one at x equals 2 and one at x equals -2. Part C, same thing. I'm going to take the denominator, set it equal to 0. X squared equals -1. Oh wait, this is the case where we have an imaginary number, right? In the case of imaginary numbers, there are no vertical asymptotes. Because the domain is all real numbers. There's nothing that we can put in there that's going to break it. Okay, and then part D. This one's the same idea, but we're just going to have to factor a little bit. So let's kind of factor it, and then also the top part is factorable too. So because we might have a hole there, we should probably go ahead and factor both of them. So the top part is pretty easy to factor. Remember, if we have a subtraction and we have a constant term and an x squared term, if those are both perfect squares, then that's going to be a difference of squares. So we can rewrite that as x plus 3, x minus 3, something that you guys probably covered extensively in Algebra 2 and hopefully as well Algebra 1, right? So that's the top factored. Now the bottom factored, we're looking for what multiplies to get -21 and adds to get 4. That's going to be -3 and +7. -3, positive 7. And look, we do have a hole here, so we're going to cancel that out. Right, because negative 3, x minus 3 and x minus 3 cancel out. So really the only asymptote here is going to be negative 7, because negative 7 plus 7 is 0. So there's going to be a vertical asymptote at x equals negative 7. The other one is a hole. There's a discontinuity there, but it's not an asymptote. So be careful with that. And that idea builds as you guys get higher up into calculus. And yeah, those of you who are doing calculus, then we talk about discontinuities, holes, and asymptotes in the very first quarter. Okay, the last one, horizontal asymptotes. There's a lot of words here, but really it's pretty easy. So the first thing I wanted to mention is that unlike vertical asymptotes, horizontal asymptotes can be crossed. They don't usually cross, but sometimes they do cross. And what they're used to do is they're describing end behavior. So it's telling us, is there a number that we're going towards at negative infinity and positive infinity? So it's pretty easy. If the top degree, if the numerator degree is greater than the denominator degree, there is no horizontal asymptote. So if the top is bigger, no horizontal asymptote. If the degrees are the same, if they're equal, then we have to divide the leading terms. So whatever our highest degree, we take the top term over the bottom term, and then it'll give us a number that will be our horizontal asymptote. And then the last one is if the degree top is less than the degree on the bottom, then we have a horizontal asymptote at 0, which is the x-axis. Okay, so let's kind of look at some here. Find horizontal asymptotes. So notice the degree here is 1. The degree on the bottom is 2. So if we look back here, the top is less than the bottom, then the horizontal asymptote is 0. So we'd have some graph, and then the horizontal asymptote would be the x-axis. So meaning if we go, I don't know, it might look like this. So as we go towards infinity or negative infinity, on the left-hand side, it gets closer and closer to 0. And then on the right-hand side, as we get towards positive infinity, it gets closer and closer to 0. Okay, part 2, degree 4 over degree 3. So if the top, if the top is bigger than the bottom, then we don't have any horizontal asymptote. No horizontal asymptote. We have an oblique asymptote, but we really don't talk about it in precalculus or even calculus, so we're just gonna leave it how it is. And then the last one, degree is the same. Whoops, I keep going the wrong way. Okay, so if the degree is the same, they're equal, right? We're gonna divide leading terms. So we're gonna take the term of the biggest on top, that would be 8. And then we're going to take the biggest from the leading term on the bottom, 4. So our horizontal asymptote is 2. So it kind of looks like this top one, except for, and we should probably say y equals 2. Y equals 2. Right, because it's going through the y-axis and it's a line. It looks the same, except for we're headed towards 2. As we go from negative infinity towards negative infinity and positive infinity. Okay, so that's pretty much it. Today just covered vertical asymptotes, which is pretty much an extension of what we did last time, right? Rather than looking for domain restriction, we just said that where the domain is restricted, we should expect to have an asymptote, unless we have ones that cancel out in the numerator and denominator, and those would be holes. And then the horizontal asymptote, it should be pretty easy. We just follow the rules, right? Top bigger, no horizontal asymptote. Top equal to the bottom, we take the ratio of the leading terms, and then if the top